Chapter 20 notes. Magnetic fields are similar to electric fields. They have the same attraction rules. Opposites attract and likes repel. And these ones are called poles. We say the opposite poles attract and the like poles repel. They have field lines. Remember, the magnetic field is real. The field lines are imaginary. We draw them to see where the field is. When the lines are closer together, the field is stronger. When they're further apart, the field is weaker. Little side note, for the Earth, in order for a compass to point towards the north end of our compass, since north attracts to south, the north pole of the Earth is actually a south pole of the magnet. So imagine that. So what's different about the magnetic fields and electric fields is on an electric field you can have a point charge that is a plus only or a minus only. For magnetic fields you have to have a north and a south. You can't have only a north or only a south. So on a magnet you can break it smaller and smaller, but there's always a north and a south side to it. So how are magnetic fields related to electricity? That was our lab today. We found out that a current moving through a wire creates a magnetic field. So here I have a wire going through here, and I have 5 compasses, and they're all pointing to the north right now. You can see the red sides are these sides pointing to the north. And when I turn the current on, they all turn, so they're kind of making a circle around the wire. And we say that that field is perpendicular to the wire or the current because the current is going in this direction and the field is going in this direction. So the field is perpendicular to the current. This field that we make with the current can interact with other magnetic fields, meaning it can attract or repel. So here I have a horseshoe magnet, and we're going to run a current through the wire. And as soon as the current goes through it, the wire turns into a magnet, and that magnet repelled and jumped out there. So this is how we draw it. The magnetic field is going from north to south, so that's the blue lines. And the symbol for magnetic field is capital B. It is a vector. It has a direction. So the field's going in this direction. The current is going through here, and those two together make a force going either downwards or upwards. If I reverse the current and go the other way, in this picture, having the current go this way, that makes the force go up. So notice that the force, the magnetic field, and the current are all perpendicular to each other. So we have 3 perpendicular lines. The field goes to the right, the force is going up, and the current is coming out of the page. This is our formula. The force is L times I cross B. L is the length of the wire that you're using, or the length of the wire that's inside the magnetic field. I, of course, is the current, and B, the symbol for the magnetic field. The current and the magnetic field need to be perpendicular to each other. If we have our wire going at an angle, that means we're going to be using a triangle and finding the perpendicular side. Right? Remember, when we do a cross product includes the sign because it's when perpendicular components interact. So the complete formula would be L times I times B times the sine of the angle. And that would be the angle between the wire and the magnetic field. A little math review. The formula for work is the dot product of force and distance, F dot D, and that means for a dot product they have to be parallel components. So F and D have to be parallel. So that formula comes out to FD cosine, where the angle is the angle between the two vectors. For today's formula, this is a cross product, and cross products are used when perpendicular components are interacting. Looking at the units, length is meters, current is amperes, and the units for a magnetic field are Teslas, which breaks down into Newton per amp times meter. Right, if I change the amperes to coulombs per second, I can switch some things around and get meters per second and coulombs. Meters per second is speed and coulombs is charge. So this makes our second formula, which is Q times the cross product of V times B. And this would be the formula we'd use for a point charge, like an electron, moving through a magnetic field. Q times V cross B. And again, it's a cross product, so we would include the sign of the angle between the velocity and the field if they are not perpendicular to each other.